Today we're going to look at electronegativity and Lewis structures for covalent bonding. Let's do a quick review. Electronegativity is the atom's attraction for electrons of another atom when in a compound. A covalent bond is formed when valence electrons are shared between atoms. So let's look at water. Water has 2 hydrogens and 1 oxygen. Oxygen has 6 valence electrons, so you can see we have drawn 6 dots around oxygen to represent the 6 valence electrons. Hydrogen each has 1 valence electron, so each hydrogen has 1 dot. Hydrogen is going to move in with oxygen and share its 1 valence electron with oxygen. So oxygen now has 8 dots surrounding it, and each hydrogen has 2 dots. Now remember, the first energy level can hold 2 electrons. So hydrogen is stable with 2 electrons because its first energy level is filled. Oxygen has fulfilled the octet rule by now having 8 valence electrons. So by sharing electrons, each atom is happy. It has a full valence or full energy level, and it is happy and stable. There are 2 types of covalent bonds. A nonpolar covalent bond is when electrons are shared equally between the atoms. So if we look at hydrogen, hydrogen shares the 2 electrons equally. So the way I like to think about that is if you and your best friend are hanging out and you're working on something, you will share that equally amongst you. You may have it for a little bit, your best friend may have it for a little bit. You work on it and you share it back and forth equally. One person doesn't have it more than the other. All right, so equal sharing, a non-covalent bond. A polar covalent bond is when electrons are shared unequally. And the way I like to think about this is if you put 2 3-year-olds into a room and you give them one toy, what's going to happen? These 2 3-year-olds are going to fight over the toy. One is going to hog the toy, is going to hold on to it, and not share it with the other kid. And that's what happens in a polar covalent bond. One element hogs the electrons more, and it does not like to give those electrons to the other element or the other atoms. So electrons are being shared unequally. This type of molecule is going to create what we call a partial positive and a partial negative, or a dipole. All right, so in this example of water, water is polar. Oxygen is much more electronegative than hydrogen. So oxygen hogs the electrons. It does not share those electrons well with hydrogen. Electrons have a negative charge. So if oxygen has the negatively charged electrons most often, it ends up with a partial negative charge. Hydrogen does not get the electrons. Now, if you remember, in an ionic bond, cations donate electrons to become a positive charge. All right, so that same concept of getting rid of electrons is going to hold true here. Although the hydrogen is not getting rid of and donating electrons, it's still sharing them because it does not have those negatively charged particles as often. It has what we call a partial positive charge. So that's what you can see here. We have our partial negative around the oxygen, and each hydrogen has a partial positive charge, all right, because of the way the electrons are being shared. So this is a dipole, all right, where we have a positive and a negatively charged end of a molecule. Water is polar, and this polarity is what makes water unique. All right, and this is one of the reasons why water has many of the properties that it has, and another reason why life on Earth is able to survive because of the polarity of water, and it makes it so unique. We can use the difference in electronegativity values, and now you will always be provided the electronegativity values for the elements, so you don't need to find a chart and memorize those. We will give you those electronegative values. All right, but we can use the difference in those values to determine if a compound is polar or nonpolar, or if it is ionic. So when we look at the difference in electronegative values, if that difference is between 0 and zero point 0.5, we say it is a nonpolar covalent bond. Therefore, it is going to share electrons equally. Between 0.5 and 1.7, we say that is a polar covalent bond, and it is therefore going to share those electrons unequally. Anything above 1.7 is an ionic bond, in which case we have a complete donation and exception of electrons. Okay, so we're going to create those cations and those anions where we get rid of or accept electrons. All right, so it's a transfer of electrons for ionic, anything above 1.7. Fluorine is our most electronegative element. It has a value of 4.0. Remember, as we move down a group in the periodic table, electronegativity decreases. As we move across the periodic table, electronegativity increases. So how do we draw a Lewis structure for a covalent compound? Covalent compounds have either a single, a double, or a triple bond. Now, each individual line represents one pair, a pair being two, electrons that are being shared. So this bond, it has one line, so we are saying that atoms share one pair of electrons. So one line represents two electrons, and this is a single bond. Here we have a double bond, meaning we have two pairs of electrons that are being shared. All right, so that's going to be 4 electrons total, but 2 pairs. Here we have a triple bond where atoms share 3 pairs of electrons. So each line represents 2 electrons. We have 3 lines, so that's 6 electrons total, but each line is a pair, so 3 pairs of electrons. We only represent a molecule using its valence electrons because the valence electrons are the only electrons that are involved in bonding. So when we write a symbol like O or S, that represents the nucleus, which contains protons and neutrons, and it also represents all inside energy levels. A single bond is the longest bond, and it's going to require the least amount of energy to break. A triple bond is the shortest bond, and it requires the most amount of energy to break. Think about this. If you have a piece of paper, all right, your piece of paper, your single piece of paper represents a single bond. It's pretty easy to tear that paper in half. Now, if you take 3 pieces of paper and you put them together, it is going to require more energy for you to tear those 3 pieces of paper apart at once. All right, a triple bond requires more energy to break. Let's look at our rules for drawing a Lewis structure. Atoms must satisfy the octet rule, meaning they have to have 8 valence electrons to be stable. There are a few exceptions to the octet rule. Group 1A only needs 2 electrons to be stable. Group 2A needs 4. Group 3A needs 6. But the overwhelming majority of the elements on the periodic table need 8 valence electrons. When we draw, our alkali metals in group 1A and the halogens in group 7A are always going to be on the outside of our molecule. Carbon always goes in the middle. Remember, electrons belong to both atoms because they are being shared. The number of electrons in your final structure that you draw must equal the total number of valence electrons for all of the individual atoms added together. And if possible, your structure must be symmetrical. It will not always be symmetrical, but if you can make it symmetrical, you must do so. All right, let's look at oxygen. Oxygen is diatomic, so we have two oxygen atoms. Each oxygen has 6 valence electrons. So I've drawn oxygen twice because I have two atoms, each with 6 dots to represent the 6 valence electrons they each have. Each oxygen has 6 valence electrons for a total of 12 valence electrons. So when drawing oxygen, I'm going to have 12 valence electrons involved in their bonding. We always start with a single bond. If it does not work with a single bond, then you move to a double. And only if you cannot get a double bond to work do you move to a triple bond. My final molecule of oxygen can have no more than 12 valence electrons because that is the sum total of the two oxygens. So I'm going to start with a single bond. I have two electrons in the center in between each oxygen to represent one pair. My oxygen on the left now has 2, 4, 6 valence electrons. My oxygen on the right has 2, 4, 6, 8. So, my oxygen on the right is happy. It has 8. My oxygen on the left is not happy because it only has 6. And again, we need to fulfill the octet rule where we have 8 valence electrons. All right, so you can see the oxygen on the left has 6 and the one on the right has 8, represented by the circle, circling their valence electrons. The 2 in the center again represent what's sharing. So this does not work. So if a single bond does not work, only at that point do we move to a double bond. So what I have done is I have rearranged my electrons such that I now have 2 pairs of electrons in the center. Oxygen on the left has 8 valence electrons, 4 in the center plus the 2 on the top and the 2 on the bottom for 8. The oxygen on the right also has 8, the 4 in the center, 2 on the top, and 2 on the bottom. So each oxygen now has 8 valence electrons, and so they have fulfilled their octet rule and they are happy. Again, double count. Make sure you have no more than 12 valence electrons. If so, you've done something wrong and you need to go back and fix it. We are going to draw any shared electrons with a single line. So I can rewrite my oxygen as seen in this example with a double bond in the center, and I have my unpaired valence electrons on the top and bottom of each oxygen molecule. Let's look at water. Water has 2 hydrogens and 1 oxygen. Each hydrogen has 1 valence electron. Oxygen has 6 valence electrons. So 1 plus 1 plus 6 is 8 valence electrons. My final molecule of water can have no more than 8 valence electrons. So when I come in and I can rearrange my hydrogens, remember group 1A is always on the outside. So I have put my hydrogens on the left and the right of the molecule to fulfill the rule that group 1A is always on the outside. Group 1A, remember, needs 2 valence electrons. Hydrogen now has 2 valence electrons and it is stable, it is happy. Oxygen also has 8 valence electrons, 2 on the top, 2 in between each hydrogen, and 2 on the bottom, for a total of 8. My hydrogen on the left is sharing 2 with oxygen, so it's happy. My hydrogen on the right is sharing 2 with oxygen, so it's happy. So everything is stable. I have 8 electrons. I have fulfilled my octet rule for oxygen. Hydrogen each has the maximum number of 2 dictated by our rule group. 1A only gets 2. So let me just redraw it here. And our shared electrons are going to be drawn in as a line. All right, so here's water. Oxygen has 2 unpaired electrons on the top and 2 on the bottom. All right, so we draw any electrons not being shared as single dots. They must always be paired together. Electrons will always appear as a pair in a covalent